but I can't find an assignment. Like that comes along with it.
Okay, that's an important part of an assignment. Yeah. Okay, well, I'll look at that, and then maybe I'll push it back, I guess.
Okay.
There was also like 9 assignments. Is that all the assignments for this time?
There were 9 assignments?
Yeah, like 9.
Oh, the 9 workbooks, like the chapter workbooks. You're talking about?
Yeah, I can't find the overview.
Well, I just put in the ones for the whole, oh, yeah. Those are for the whole semester. So the only things that you're assigned are the ones that I give on the announcements. So look at the announcements and it'll tell you which one of those to do each class. Okay. Yep. All right. Who remembers what we were working on last time, what we talked about?
Moments.
That's right, moments. So I introduced moments. We're talking about two-dimensional rigid body statics now. And so now I want to talk about a specific kind of moments, and I want to make a really clear distinction between the moment of a force and what we're talking about right now is the moment of a couple. Okay, so we're talking about couples, and couples you treat as moments, but they're a very specific kind, and they have their own characteristics. So a couple is 2 equal and opposite forces acting at a distance from each other. So for example, if this is a body and you have a force F going this way and a force F going this way, that's a couple. They're parallel to each other and acting in opposite directions. And the key thing about a couple, and I'm going to show you how this works, it's surprising, is with a moment, remember the moment of a force, what you choose as your about point totally changes what the moment is, right? So in general, a moment, and in parentheses I'll write of a force, depends on the choice of about point. The moment of a couple I'll put that in parentheses because I'm usually just going to talk about moments, and that means moment of a force, and couple means moment of a couple. Doesn't depend on the about point. In other words, you get the same moment for a couple no matter what your choice of about point is. Okay? So the moment is the same no matter what about point you choose. So I'm going to just go through a little proof so you can see how this works. It's really surprising. But what this is going to mean is that instead of talking about, so when you see couples on a free body diagram, they're not going to tend to be drawn as equal and opposite forces. They're just going to tend to be drawn as a pure moment, because you can choose any about point and it's still the same moment. Okay, so here's what we're talking about. So let's say we have this body, arbitrary body, and let's say we have a point 1. So P1 there, and a second point, P2, okay? And there are equal and opposite forces acting at P1 and P2, okay? So we're going to call this force the vector F, and that means we can call this one the vector negative F if they're equal and opposite. It's just all the components are negative, okay? And now let's choose the location for an about point. Why not here? Okay. Well, we're going to calculate the total moment produced by this couple. And what we're going to see is we're obviously going to start with the coordinates of A showing up. But by the time we're done simplifying it, A is going to disappear. It doesn't matter. Okay. So let me say the coordinates of A will disappear from the expression of the total moment. Well, remember that for the definition of the moment of a force, you have the rho crossed with the force vector. We have the force vectors here. The rho vector that you need is the vector that goes from A to where the force is applied, okay? And so I'm going to draw for the force F, this is our rho vector. Okay, it goes from A to where the force is applied, so I'll call that rho 1. And for our force negative F, this is our rho vector. Call that our rho 2. Okay, so that's just using the definition of the rho vector from last time. And the total moment about that, around that about point A, is rho 1 crossed with F. Okay, that's the definition of the moment of that force F around that about point A. And then if we're doing the total moment, we also have to do the moment applied by that force negative F, and that's rho 2 crossed with our other force, which is negative F. Okay. And now let's use the definition of those rho vectors. So if A is the coordinates of that about point A, and say P1 is the coordinates of that point P1, how would we come up with a vector? How would we express that rho 1 vector in terms of those coordinates? We've been doing this in the vector review.
Just change the origin to A.
That's one way you could do it, but since we already have those coordinates, we'll just write that row 1 as P1 minus A. Okay, that's the second way to do it. So MA total is P1 minus A, whole quantity, crossed with F. And then row 2 is the quantity P2 minus A. And we're crossing that with negative F. And cross product is distributive. So we can write this as, just distribute this all out, and you have the coordinates of P crossed with F minus the coordinates of A crossed with F plus the coordinates of P2 crossed with negative F minus the coordinates of A crossed with negative F. Well, I haven't pulled that second negative out, but this is right.
Oh,
And now you can pull those negatives out to the front. So this turns into P1 cross F minus A cross F minus P2 cross F plus A cross F. And this is the step where you can see where that dependence on the about point goes. This cancels with this. Okay? And our expression for the moment no longer has anything to do with that about point. It doesn't matter what the coordinates of that about point are, the answer is the same. And now you can, simplify it, and you get something that looks like this. P1 minus P2 crossed with F. Remembering that isn't so important. But the moment produced by a couple is the vector to the point where F is applied, from the point where negative F is applied, and then crossed with F. Okay? So you get the same MA total for any about point coordinates. And so that means that we're just going to think about couples as pure moments. When we represent them in 2D, we'll represent them as like rotational arrows like that or that. Okay. And in 3D, we'll represent them as vectors, but with double heads on the arrows. So if you don't know anything about the direction, you'll represent it like this, the same way that we did for force vectors, except that these arrows have double heads for the two forces because it's a couple, or if one of the components is 0, and you only have, say, two components, this is one that has, like, say, a y and a z component only, no x component. Okay. What does it mean if a couple has only a y and a z component? So remember that what we're talking about with moment vectors is like an axis of rotation. It's a right-hand rule thing. Okay, so if it has a component that has like a y and a z component, you know, like this, that means your thumb goes that way and the rotation happens in a plane like that. Okay. So the components of the couple are always your thumb in the right-hand rule. So the components of a couple or any moment including couples are the thumb in the right-hand rule. Yeah.
Remember the direction of the arrow pointing for your thumb there?
That's right. So if you want to envision it as a rotation, which is easier to process, yeah, your thumb goes in the direction of the vector, and then your fingers tell you the direction of the rotation. Okay, well, let's do a calculation. So this is a 2D rigid body problem. So let's say we have a circular body and the radius is 0.5 meters. And over on the right side, there's a force vector in that direction. We don't know the magnitude, so I'll call that F2. But we do know that it's acting at 30 degrees with the horizontal. And let's say on the left side, it's a totally unknown force vector. So I'll call this the force vector F1. And then down here, let's say that there's a couple applied. That's the default direction, and let's say that it's negative, which means really, and it has a value of 450 Newton meters. Okay, which we could write exactly equivalently with the arrow going clockwise, and that is a positive 450. Okay, that's what those negatives mean. And we're going to do this calculation twice. We want to calculate that force F1 and that variable value F2. And we want to do it using an about point A, where this is A. Okay. And then second, we want to do that same calculation using C for setter. I don't know, not C for part B. Okay, so we haven't done a lot of statics problems yet. We've mostly just talked about rules and stuff. But what do you expect the answers, what do you expect for the relationships between the answers for part A and B? They're going to be the same. In statics, you can choose any about point to do your calculations, and you'll get the same answers. Okay, so even though every one of these, these forces, F1 and F2, are going to produce different moments about A and about C, in the end, our answers for the forces are going to be the same. Okay? So for part A, I'm going to write out this row force moment table. And we're going to go through all three of those loads. So I'll do F1 first. If our about point is A, what's the row vector for F1? The radius of that circle is 0.5. So you'd go negative 0.5 for X, and then negative 0.5 for Y. Do you see that? If we're using like a normal coordinate system, like this. So I'll write this as negative 0.5, negative 0.5, and I'll keep it in 3 dimensions for now, just for a while as a reminder that all these moments are 3D vectors, even though in 2D they only have Z components. The force vector, we don't know anything about it, so it's just going to be X and Y components of F1. No Z component. If you take that cross product, you get negative 0.5 F1Y plus, sorry. I'm going to write the X and Y components first. Those come out to be 0. Because if you cross out for the X component, cross out these two, you get this times 0 minus 0 times this. Okay, so X component comes out to be 0. The Y component, cross out the Y components, something times 0, 0 times something, so that's 0. The only one that's non-zero is cross out this, negative 0.5 times F1Y minus negative 0.5 times F1X. Okay, with me on that one? So now we'll go to this force F2, where we know the direction. What's the row vector? So our about point is A. The row vector is the vector from A to where F2 is applied. I think maybe you're going from F2 to A. You have to go from A to it. So you have the right idea, but those are both switched. So you go positive 0.5 and then negative 0.5.
Oh, yeah. Get that back to the whole problem. It used to rise and run.
Oh, yeah. Yeah. It just takes a while to make this all muscle memory. Okay, and now that force vector. So how are we going to come up with a force vector that's in that direction with a magnitude of F2?
X cosine theta.
Yep. So we're going to go F2 times cosine of theta, F2 times sine of theta. And now what's our theta going to be? Yes, 150, exactly. So that's going to come out to be, I'm just going to do all that, 0.866 F2, positive 0.5 F2, and then 0 for Z. And now we take the cross product. X and Y are zeros. The Z component is 0.25 F2 minus 0.433 F2. So I think that comes out to be negative 0.183 F2. That's what I have written down here anyways. Any questions about that one? There's one more load we have to deal with, and that's the couple. Remember, the couple doesn't depend on the about point at all. And so for couples, you can forget about rho, forget about force, and we just treat it as a pure moment. So this is the 450. A positive Z component of a moment would be this way. So that means a counterclockwise moment. So that's the default that we're using. And so the Z component of this moment is just negative 450. Okay. Any questions about the sign on that? Yeah.
Not so much a question or like confusion, but why would you write a negative moment with the counterclockwise?
Yeah, it's sort of the same thing as like drawing vector components, because this is the positive Z moment. That's why, you know.
Okay.
But so like it's about the same as if you drew the X direction this way and the Y direction this way, and then put negative components there, you know. But I could have just as easily done it clockwise. But then it actually would have taken more figuring if I would have done that, because then you have to say like, oh wait, that's clockwise, so it has to be negative in the Z component. So negative 450 is the Z component. All right, well now we're going to use Newton's second law and the moment equation. Newton's second law says we add these all up, it has to be equal to 0. The moment equation says add these all up, and it has to be equal to 0. So this table just puts it right in front of us. So Newton's second law says F1x, F1y, 0, plus negative 0.866 F2, positive 0.5 F2, 0 is equal to zeros. The moment equation, rotational Newton's second law, says 0, 0, negative 0.5 F1y plus 0.5 F1x plus 0, 0, negative 0.183 1.83 F2 plus 0, 0, negative 450 is equal to zeros. Do you remember when I said how many equations we're going to get for rigid bodies in 2D and 3D? In 2D, I said we're going to get 2 useful equations from Newton's second law and 1 useful equation from the moment equation. Okay? Well, here you can see it. I mean, we do get a third equation from Newton's second law, but it just says 0 equals 0. That doesn't help us solve anything, so you can forget that one. So moment equation, we do get x and y equations, but they just say 0 equals 0, so they don't help. So you can forget about that one and that one. And all you have left are x and y components for Newton's second law and a z component for the moment equation. Okay? So let's write out this system of equations. So we have the first one, f1x minus 0.866 f2 is equal to 0. The second equation says f1y plus 0.5 f2 is equal to 0. And the third one says negative 0.5 f1y plus 0.5 f1x minus 0.183 f2 is equal to 450. I moved that 450 over to the other side. Okay, well, you could solve this through a complicated system of substitution, but it's easier to just plug it into reduced row echelon form. So let's write this out. We have 3 equations, 3 variables. Okay, look at the variables and make sure we can solve it. f1x, f1y, and f2 are 3 variables, so you can solve that with 3 equations. So our augmented matrix has 3 rows and 4 columns. Here are the equations. For the variables, you can do any order you want, but I guess I'll use this one. The last column does have to be the constants. Okay, so for equation 1, f1x has a coefficient of 1, f1y has a coefficient of 0, f2 has a coefficient of negative 0.866, and the constant is 0. Equation 2, f1x has a coefficient of 0, f1y has a coefficient of 1, f2 has a coefficient of 0.5, and the constant is 0. And the last one, f1x has a coefficient of 0.5, f1y has a coefficient of negative 0.5, f2 has a coefficient of negative 0.183, and the constant is 450. Yeah, that's So that's 0.5 times 0.5 F2 minus 0.5 times 0.866 F2. And if you solve this, if what I have written here is right, and actually, yeah, if anyone would mind plugging this in and making sure this is right, that'd be awesome. So F1x, I think, comes out to be 779.4 newtons. F1y comes out to be negative 450 newtons. And F2 comes out to be 900 newtons. And these two give you the vector, so the force vector F1 you can think of as 779.4 negative 450. Can anyone confirm that or deny that?
Is that what we went up with?
You got the same thing? Good. Okay, let's do it again with the new about point, and just you get to see once with your own eyes that the statics answers come out the same, even though all the steps are different if you choose a different about point. Okay. If it doesn't come out the same, I quit. I'm going to go find another job. So this is high stakes for me. So I can't really do anything else. Okay, so part B. Maybe I'll skip some of the steps this time so it doesn't take quite as long, but same idea. I'm still going to fill out the table. This time I'm going to fill out, for the forces and the row vector, I'm just going to fill out X and Y components. For the moment, I'm just going to fill out the Z component, but you just have to remember that this is what it means when I do it. You can think of them as all having 3 components, just with zeros. Okay, row, force, and then moment about C this time. So first, F1. Okay, so what is the row vector if our about point is C for that force F1? Negative 0.50, yep. You're starting at the about point and going to the force. So negative 0.50. The force vector is the same as it was before, F1x, F1y. And the cross product is negative 0.5 F1y. And I'm only keeping track of the Z component. Then for F2, what's the row vector for that force? So start at C and go to where F2 is applied. 0.50, yep. The force vector is the same, so that's negative 0.866 F2, positive 0.5 F2. And so that cross product is 0.25 F2. And then last is the couple. We don't care about these things because a couple, it's equal and opposite forces. It produces, so it adds up to 0, and we don't care about the row vector, and we get a value of negative 450. So I'll just go straight to the equations this time. So add up the x components, they have to be equal to 0. And again, that's just, adding up the vectors in the force column. So we got F1x minus 0.866 F2 is equal to 0. The second equation says F1y plus 0.5 F2 is equal to 0. And the third equation, this is the z components of the moments, says negative 0.5 F1y plus 0.25 F2 minus 450 is equal to 0. I'll move that over to the other side. And so our augmented matrix I'll use the same order of variables, F1x, F1y, F2 constant, and the equations 1, 2, 3. So for that first row, we have 1, 0, negative 0.866, 0. For the second one, we have 0, 1, 0.5, 0. For the third one, we have 0, negative 0.5, positive 0.25, 450. Those equations look different than we did in part A. Well, the first two look the same because it's just forces, but the third one looks different. The moments all look different because we chose a different about point. So I don't have this in my notes, but could a couple people compute these? And I hope they come out the same. Yay. So you get that F1 as a vector is 779.4, negative 450. That's in newtons. And F2 is 900 newtons. So now we're really close to doing, this is really close to 2D rigid body statics, and to do 3D rigid body statics, it's really not any harder. You have to know the third component of your row vectors, the third component of your forces, and then when you take a cross product, you have 3 components of the moment, so you have more equations to plug into row echelon form, but conceptually it's exactly the same. The last thing that we have to do now is, notice if you're trying to calculate the forces that are holding this disc, imagine that this is a problem you're trying to do, and that's like a carousel on the ground, that they used to have at parks. I don't know if you've ever even seen those anymore because they kill kids. Yeah. But we used to do that and get hurt all the time. But So if you're trying to calculate those forces that would put this in static equilibrium, the problem doesn't appear to you like that. The problem appears to you like you have some kind of joint here and some kind of joint here, and you have to know how to go from the physical joints to what kind of loads they apply, okay? And then they end up applying loads that look like that, maybe, you know, in certain cases. But so that's the next thing we have to do is just go through the whole list of two-dimensional joints and say, when you see this kind of joint, just like we did for particle statics with cables and frictionless contact and friction contact, now we have to say, okay, there's all these new kinds of joints, pin joints, what are there in 2D? There have to be other ones, but pin joints, weld joints, and when you see those, what kind of loads do those translate to in your free body diagram? So that's the only step we have left, and then we'll be doing any kind of rigid body statics problem. So next time we'll go through the whole list of joints. Any questions? Okay, so there's definitely some problems I can give you for this. I'll look at I don't know if I meant to give an assignment or what happened there, but I'll look and find out about that. Okay, see you Friday.